Hey, once anyone's class. So I know last time we talked about the difference quotient, and I just want to clear up one thing I didn't talk about in the last video, and that what is it? What is the difference quotient? So let me start off by putting a couple points on here. This is x, okay? So we'll just call that x. And then remember the y coordinate. If you plug in a value from the number line from the x-axis, and you plug that number in, the y coordinate associated with that point is what we call f of x. Remember, f of x means the output when x is the input, which is just another way to say y. Well, if I add h to x, right, h being some positive number, if I add h to x, that means we took our starting point and we shifted over from where we started to where we end up. We shifted over by h units. So we're at x, now we're at x plus h, so we move to the right h units. So there's what x plus h looks like on the number line. It just means we move to the right whatever h is. But then remember, if this is the input, the y coordinate associated with that is what we call f of that input. So this is f of x plus h. Alright, so f of x plus h. Now, if I draw a line connecting these two, I'm going to draw it blue. If I draw a line that connects these two dots from x f of x to x plus h f of x plus h, I'm going to dash that line just because it's not really there. Just saying hypothetically, if I did connect those 2 points with a straight line. Any line, we can talk about the slope of that line. And if you remember, the slope of a line is found by the change in the y's. So like, remember y2 minus y1. You may remember this formula, you may not. But anyway, the way we find it is subtract the two y's and then subtract the two x's and divide. You know where this was x2, y2. And this is x1, y1. And that's how we found it. But we're using function notation. We're not using x's and y's. We're using x's and f of x's. So what would we call it? This time we'd call it x plus h as our second point, and f of x plus h. And we call this x f of x. Okay, so y2 minus y1 would become f of x plus h minus f of x. Alright, and then x2 minus x1, that's x plus h minus x. But if we simplify this, the x's cancel, and we're just left with h. So there's the difference quotient formula. And where did we get it from? We got it from plugging in these 2 points from just the graph of any function into the slope formula. And these 2 points just happen to be just 2 random points that are h units apart on any function. So what the difference quotient is, it's just 2 points on the graph of any function connected with a straight line, and it's the slope that would connect those 2 points. Okay, so that's what the difference quotient is. It's just, yeah, this function did dip down and go back up, but if we connected those 2 points with a straight line and kind of bypass going down and come back up, that slope is the something we call the average rate of change, which is also in this section. The average rate of change between the 2 points. Okay, now average rate of change, I didn't really give you notes on it because it's literally is the difference quotient. The average rate of change is f of x2 minus f of x1 divided by x2 minus x1. So if you're ever told to find the average rate of change, the only thing that's different between what you did before and what you're doing now are these 2 points and what we call them. What you're doing with an average rate of change problem and what you're doing with a difference quotient problem. Now this becomes f of x1 and this becomes f of x2. Okay, the only difference between x and x plus h and x1 and x2 is x1 and x2 are just going to be specifically given to you. This might be, like for instance, this might be 1, this might be 5, this might be 2, and this might be 6. Okay, and then f of x2 minus f of x1 would be 6 minus 2 over 5 minus 1, which is 4 over 4, which is 1. And the average rate of change would then be 1. Alright, but that's the only difference between the difference quotient and the average rate of change. Is typically the average rate of change, we just get a number because we know specifically what all these values are. The difference quotient, this is h, and we don't know specifically what h is. And we end up getting an expression for what this slope would be, rather than getting an actual slope like we are getting right here. Alright, moving on. Section 1.6. This is we're bypassing 1, 4, and 1, 5, which are linear functions, which should be a review if you don't remember a lot about functions like how to find slope. That slope formula that I just showed you, if it was brand new to you, if you've never seen it before, then you need to go back and review section 1.4 and 1.5. If you don't know how to find parallel lines, if you don't know how to find perpendicular lines, then you need to review those 2 sections. Alright, 1.6, transformations of functions. Here's a summary of the transformations of functions from our textbook. Alright, I scaled it down there so it would fit. But these are common graphs. These are what I call the base functions. Now the base functions are what we're going to use for our functions project. So it's very important that you understand how the base functions work. Okay, but the base functions are f of x equals c, c meaning just a constant, just a number. Alright, no x's are involved. Alright, f of x equals c, y equals c is just a horizontal line, always. Let me pull in our graphing calculator in here so you can see it. But if I literally just type in on here y equals, clear all this stuff out. That's from where we did our piecewise functions in the last section. If I just like pick a number like 7, y equals 7, I graph it, it's going to be a horizontal line. And it literally means that trace lets you put a cursor on the graph. If I plug in any x value, notice all the x values are changing. Y is always 7. That's what y equals 7 means. No matter what I make x, y equals 7. Alright, now we first talk about this in this textbook in the section that we skipped, 1, 4, 1, 5. But moving on, let's go to the y equals x. The identity function, y equals x, is this diagonal, these angles here, like the y-axis to the x-axis is a 90-degree angle. Y equals x cuts that in half, so these are like 45-degree angles from the x-axis up to that line. So y equals x, it slices what's what we call quadrant 1. This is what we call quadrant 3. 1, 2, 3, 4. It slices those right in half, quadrants 1 and 3. Comes right through the middle of those. This is going to be an important line for some later chapters. 1.8, I believe. We use y equals x to flip graphs over. Anyway, domain and range, just like it was before, these are the sets of all the x coordinates on this graph. these are the sets of all the y coordinates. So every x can be represented on this graph, every y, and it's always increasing. Okay, odd function. Remember we said y equals x. Y, the x powers are always odd numbers for odd functions. So x to the first for these polynomial functions. So it's an odd function. All right, absolute value. Absolute value means distance from 0. So notice 1 is 1 unit from 0. Right? 2 is 2 units from 0. 0 is 0 units from 0. But -1 is also 1 unit from 0. Right? Its distance from 0 is positive. -2 is 2 units from 0. So it's a distance function. And because it's distance, we're always getting positive values except for at 0, or we get 0. Distance from 0 is 0. So the domain is at -infinity to infinity. The range is 0 to infinity. It decreases until it gets to 0, and then it starts increasing. All right, it's an even function because of that symmetry at the y-axis. The way we get absolute value, the easiest way, it's actually stored under math and number. Okay, so there's absolute value. So absolute value of x. So there's that graph. But the easiest way to get it is under catalog. It's the very first thing in catalog. So right there's ABS for absolute value. So if you need to get it, if you need to use an absolute value in a graph, just know that it's there for you. All right, and then quadratics, we'll talk a lot about those in chapter 2. And cubics, they're what we call polynomial functions. Where they don't have this straight line behavior anymore. They bend, they start bending. And the higher and higher and higher the power on these polynomials, the more and more bends that they get. All right, so squares, square root, cubes, cube roots. Okay, notice that a square root, if you take the square or the quadratic and you rotate it 90 degrees, you only get the upper half here, meaning this part right here would be the only part that we see that shows up if I rotated this 90 degrees. But if I rotated this, you kind of have to rotate it and then flip it. All the parts of the cubic show up in the cube root. Okay, and it's because you can't take the square root of a negative number. Okay, you can't square a number and get a negative, so you can't take the square root of a negative. So it has a restricted domain and therefore a restricted range, where the cube root, you can take the cube root of -8. Cube root of -8 is -2. It's fine. So we get -infinity to infinity for domain and range there. All right, so notice all of these functions are evens or odds except for the square root function because of that property. All right, it's not an odd function or an even function because it doesn't have that y-axis symmetry, and it doesn't have an odd symmetry because it's not an odd function. It doesn't have that. It can't have negative inputs go into it. All right, but these are the base functions. What we're going to do in this section and what we're going to do on your functions project are start off with something like this, a line, and move it up, right, down, left, whatever, stretch it, flip it over an axis. Any of these can be stretched, flipped, rotated. We don't really get into rotating in this semester, but we will flip them over an axis and move the vertex and all the other points on the graph around in the plane. That's what this whole section is about.